that refer to their phosphorus slips back here on the table that we can fill out.
Yeah. I apologize.
Well, did you have a nice lunch?
Yes. Did you?
I had a little bit. You don't want to eat too much. Postprandial narcolepsy. I want to fall asleep on my feet. This is the last little piece. I don't think I showed this slide. This was one of those speech deprivation studies that was done. And this was in 1211, Ferdinand, Emperor of Germany, in an attempt to discover the natural language of God, raised dozens of children in silence. God's preferred language never appeared, and the children never spoke any language and all ultimately died in childhood. This is how important that external stimulation is. And it really determines brain structure and brain chemistry. So here is just deprivation of language. And we know we know now what a driver that is for brain development. So, for example, children with autism, have delayed speech, and that sets up a whole panoply of interactions in the brain because speech is such a driver of sociality for children, the ability to communicate. And so just looking into someone's eyes is an amazing way to communicate. And if you avert your eyes, because this is part of your autistic profile, then the ability to actually communicate with fellow human beings and to benefit. Remember we talked about sharing of minds, and this helped neural integration and helped a number of other things. Probably there's a dozen other bars we could have put on that graph just to show you how important the sharing of stories is and language itself is. Now we said we would get to this poem that was written by Emily Dickinson. So what I'd like you to do is just kind of if you can read it, read part of it anyway. Actually, read it all, because the last part's the best. It's an amazing insight. Can you see it? Can you read it?
Read it out loud.
Oh, yes. The brain is wider. Now, this is an important thing, too, because I'm going to read it. This is a male voice reading this. And then you're going to see something else that should activate other pathways in your body that really allow you to fully perceive, the importance of what Emily is talking about here. So this is the plain old male voice reading something very profound, which sometimes works and sometimes doesn't. Okay, the brain is wider than the sky, for put them side by side, the one the other will contain, with ease, and you beside. The brain is deeper than the sea, for hold them blue to blue, the one the other will absorb as sponges buckets do. The brain is just the weight of God, for lift them pound for pound, and they will differ if they do as syllable from sound.
The brain is wider than the sky, for put them side by side. The one the other will contain with ease, and you beside. The brain is deeper than the sea, for hold them blue to blue. The one the other will absorb, as sponges buckets do. The brain is just the weight of God, for heft them pound for pound, and they will differ, if they do, as syllable from sound.
We'll pick up right there in a couple minutes, but I just have a couple things to add to that. Let's just talk about neurons in the brain. Neurons are the nerve cells that make up the brain. There are a few of them scattered here and there, and we'll just take a look at numbers. There are 100 billion nerve cells in the brain. That's 10 multiplied by 10, 11 times. There are 2 million, what should go after that one? 2 million feet, miles, 2 million miles of neurons in the brain. This is if you put all the parts of the neuron together, that is the long axon and the more fibrous dendrites that reach out to connect to the axons. I meant to change that red text to yellow, but I'm sorry I didn't do that. They're about, if I'm a neuron, okay, so I got a Facebook account, and I got 10,000 friends. I don't have 10,000 friends on my Facebook, but you have 10,000 connections for one neuron with other neurons, just to give you some idea of the level of complexity that's involved in the brain. And so if you actually take the number of connections, which is 10 to the fourth, and include that with a number of neurons, you go add the 11 to the 4, you have 10 to the 15th. So this is 10 multiplied by 10 is 15 times. And then, if you determine the number of possible on-off events from all these connections, whether on or off, and the possibilities there, on-off firing patterns are 10 to the millionth. So it would take a few months of your life just to count that far, I think. But it's amazing how well the brain works and the degree of fidelity with which it can actually remember stories and events and people's faces and names. And we know that the ability to actually retrieve has a tendency to be correlated with increased age. It's unfortunate it doesn't happen the way we would like it to happen. The older you get, the more you can remember about your past. But unfortunately, you have to wait a couple minutes to walk around and do something else, and then it pops into conscious memory. So you can... All right, so now we'll pick up another segment of that same piece, that same video.
A baby's brain. Less than 1 pound of gelatinous tissue. And within its milky, convoluted folds, a universe of meaning. Emotions, ideas, memories, dreams, all will somehow find a home here, evolving and changing over a lifetime.
The ultimate machine and the ultimate source of everything. We understand the world the way we do because of the brains we have. We will understand the brain itself the way we will because of the brains we have.
The brain is the most complex thing on Earth. Even the brain of a baby is wildly complicated.
A piece of the brain, the size of a grain of rice, contains about 10,000 nerve cells, just in that little piece. And you can just imagine how many pieces you have in your head. Within that 10,000 nerve cells, each nerve cell can make anywhere between 1 to 10,000 connections with other nerve cells. So there are something like 1 trillion connections.
It's almost overwhelming to think about the whole thing. If you think about how the whole brain and nervous system gets assembled, you just want to throw up your hands and say it's way too complicated, we're never going to understand it. The brain is the seat of our consciousness, of who we are. And in understanding where it comes from, we understand where we come from.
All right, the first phase of brain development is, it's called neurogenesis. And if you look at the picture of the brain, you always see some hollow spaces in the brain that contain cerebral spinal fluid. And so in early stages of development, there's actually tissue that surrounds the interior of those ventricles, primarily the 2 lateral ventricles, the 2 biggest ones that are toward the front of the brain. And those cells are stem cells. And they are the ones that are actually going to form the brain, different parts of the brain. But one of the things that they need to do initially is to be born. And then what they become is determined to some extent by who you are. Now, we're not talking about facial looks, or we're not talking about, you know, having brown hair or green hair or whatever kind of hair you want to think about. But what we're talking about here with this kind of development is just getting cells where they need to go in order to communicate with who they're naturally supposed to communicate with. So the first part then is the neurogenesis, which means literally the beginning. So this is the beginning of the nerve cells. You got that? Should be sound for that.
Divide again. Within 3 weeks, the multiplying cells have curled into a quivering oval ball. Inside lies a cluster of cells that have begun to fold themselves into the shape of a garden hose, the neural tube. From the bottom will come the spinal cord. From the top, the brain. Here lies the primitive beginning of all our thoughts and feelings. By 4 weeks, just as a woman is discovering she is pregnant, the first brain cells, the neurons, are already forming at an astonishing rate. 500,000 neurons every minute. Neurons that will never reproduce themselves and rarely be replaced.
All right, just very general anatomy of the brain, the parts that we'll be talking just a little bit about today. This is the cortex. It's the part of the brain that invests, you know, the inside of the cranium. Though it's only about 5 or 6 millimeters thick, but because it has so many folds, it looks like it's actually, you know, takes up more space than it does because it looks actually larger than it actually is. But if you were to spread it out flat, it would fill like a kitchen table. So once all those folds are straightened, it is a fairly large surface area, but it always looks thicker than it is because of the way the brain has formed itself. But if you look at the early development, it's totally smooth. There are no wrinkles. There are no, you know, they call them gyri, or the bumps, and the sulci or the sulcus is the groove in the brain itself. So what we're going to talk about somewhat is the neocortex. The reason we're going to talk about that's really the newest part of the brain, developmentally as far as evolution is concerned. And the other areas that are important to us are the limbic system, which is this area right here. Limbus means to surround, so you can see kind of the structure of the limbic system determines the name to some extent. And then the midbrain, that's between the limbic system and actually the brainstem, and then the final part here is the brainstem. So there's a lot that goes on, for example, between the mother and the baby in the process of, for example, nursing. So, and some of this is based upon contingent communication between the mother and the baby. That is, if the baby is uncomfortable and the mother has attended to the needs of the baby over time, she can pretty much determine whether the cry is from being hungry, from a wet diaper, from something uncomfortable that's scratching them, or just from being too hot or too cold. And over time, for example, let's just imagine that the mother's, you know, the baby's like 2 or 3 months old, and the mother has decided for whatever reason to do bottle feeding. Same holds true for breastfeeding, but this fits a little bit better with an example of the baby being uncomfortable, and the mother senses this is the noise the baby makes when the baby's hungry. So the mother leaves the room, and the baby's like in some kind of crib or playpen area, and is watching the mother leave. I mean, the mother comes over, looks at the baby, and then leaves. And so the baby watches the mother leave, and you would think that the baby would cry more. But if the mother is contingently communicating with the baby has already been primed that this movement of the mother is going to result in something positive. So even before the mother gets back with the bottle, the baby is calmed. So this process can go on, you know, day after day, month after month, year after year, year after year. But specifically with the feeding and the holding that's involved and the gaze. I mean, I didn't experience this with my own 3 children, but I did experience it with the grandchildren, particularly the youngest one, because when you were feeding him, he would look into your eyes, and it was just an overwhelming gaze, and it gave you such a feeling of well-being and calm that you were wondering if you were doing the same thing, you know, in this case for Dominic. So what's going on here, though, is actually there are for the baby and for the mother, and to some extent for the fathers, because the fathers have oxytocin too. What happens is that for the baby in particular, you have a release of oxytocin, which is the same molecule that causes the walls of the uterus to contract during delivery and causes the ductals in the breast to express milk. Okay? It's also called the bonding molecule, because there's always an exchange of insulin secretion between 2 people in any affectionate kind of situation. Or the love molecule, that's another name for it. In fact, they do studies with people in groups, and they put a mist of oxytocin in the air, and the people get along a lot better than they would, you know, under control. So if your husband's grumpy, you know, just get a little squirt bottle aerosol, you know, and but oxytocin also has some fantastic properties as far as being able to ensure the development of this part of the brain, which is where your fight-flight mechanism is. It has an ability to actually create a sense of safety and security in the baby as a result of this interaction between the mother and the baby, or the grandfather and the baby, or whoever else is involved in caregiving. So there's a dynamic that goes on there, and that persists unless there's some kind of event that's traumatic and persisting, because it has to be of certain duration and certain intensity and a certain time in the child's life to be able to change this process. But this is the first thing that can happen as far as that relationship is concerned, and this is called attachment. It's the most important relationship that anyone has in their life, the initial attachment to a kind, compassionate caregiver. If you don't have a kind, compassionate caregiver, there's another kind of attachment. Okay, so this is a positive kind of attachment. And there's a whole science devoted to just the attachment process itself, and how destructive an insecure attachment can be, or a disorganized attachment can be for the child. So we'll just take a look quickly, because I want to talk about this a little bit later on, but I'm not going to spend much time on it now. So there's a lot of different functions for these areas of the brain. So this is involved in a lot of cognitive processing. You know, we have, for example, the area that's involved in the kind of memory that is involved in executive functions. So it's like switching from task to task, being able to focus, regulating emotions and things like that to some extent. And then there's a limbic area and the midbrain area. I just read a paper, actually it was a chapter in a book, about these 2 areas, and they're not quite sure the contribution of them together, what the percentage is, but they know, for example, that if these areas are underdeveloped to begin with, or have their structure changed as a result of exposure, for example, to violent video games, that there is a syndrome that they've recognized now, because one of the things that this area is responsible for is to act as a barrier against the release of anger or aggression. So violent video games have a tendency to diminish that natural resistance to an aggressive act or a violent act. And they call this syndrome, you know, we're all familiar with AIDS. Okay, so basically it's an acquired immune deficiency syndrome caused by a retrovirus. But it doesn't actually kill the person. What kills the person is the fact that it interferes with the immune system. primarily cells called T helper cells, but there are others involved too. So they've actually named this acquired violence autoimmune deficiency. In other words, you've acquired a deficiency in the part of your brain that was to regulate your ability to control yourself, to respond in a way that's contingent with the stressor you're being exposed to, and not to include as a choice a violent or aggressive act. So this modulates that process. So this just shows you, here's someone that's seemingly somewhat fully developed, although there's a lot that goes on in the teen years as far as development. In fact, they've broken down the first 12 years is the first 12 years of life. The second 12 years is adolescence. They say it ends at 24 now, so it begins at 13, ends at 24, because there's so much brain development going on. In fact, the teenage brain doesn't have a lot of the fatty coating that covers the axons of the neurons. It's like if you had a wiring closet down in your basement and you had all these copper wires, but they didn't have any of the plastic insulation on them. There would be a lot of short circuits. It wouldn't function very well. The electricity wouldn't flow very smoothly back and forth, and you'd have a lot of dropped information, so to speak. So the same thing goes on here with the teenagers in the sense that they don't have the pervasive myelin covering for some of the neurons in their brain. In fact, the majority of them are really going to get myelinated, between 18, 19, 20, all the way up to 24. That's when it finally ends. So what the myelination does is it actually increases the speed of conduction in the neuron 300-fold. So they're more efficient at processing information. In the middle of all that, they start to do pruning. That is, they start to get rid of neurons because they want to refine what's going on in the brain. So this whole process makes them vulnerable to a lot of addictions. You just name it, and this actually creates a potential vulnerability for some of the addictions like drug addiction, even pornography, and things like that. So there's a lot of research going on in that area. But they're finding basically that this process that goes on in the adolescent brain is necessary, but it also produces a lot of very, very positive results, other than what I've just talked about now, such as the myelination and the ability to communicate better and the refining of the neural network. So they're more efficient at processing information. So this is the hierarchy that we kind of looked at in the brain, starting with the neocortex, limbic system, midbrain. Brainstem actually controls a lot of our automatic functions. So if you're running and your CO2 level is up, you need to breathe in more oxygen, you don't have to go through the process of saying, okay, now I got to do 14 breaths a minute or 72, my heart rate should be 72 or whatever. This is done automatically for you. But if someone takes, for example, a narcotic, there's an area in this part of the brain that actually monitors the level of carbon dioxide in the blood. So if you take heroin, or an overdose of Percodan, Percocet, oxycodone, then what happens is that this area becomes less sensitive to the level of carbon dioxide in the blood. And so when you have a heroin overdose, you usually die of asphyxiation because of this very process that takes place in the brainstem. So it's very important at maintaining some of those automatic functions that we sometimes forget about. So we'll do a little bit just on the cytoarchitecture. There's a couple little video clips here from that same series that we just showed you. But you can see here, and this is like really wide open, because this is absolutely packed when you look at, for example, a cross-section of the cortex. But this is just illustrating a nerve impulse. And this would be the cell body where the DNA is. And the thicker fibers would be the axons, and the thinner ones would be the very fine dendrites that help to form those 10,000 possible connections that are made between one neuron and another.
billions of brain cells are not done forging links with billions of other brain cells. Eventually, there will be trillions and trillions of connections between cells, charged with electrical pulses rippling like lightning storms across the hills and valleys of the brain's deeply furrowed tissue. Every cell in its place, every link between cells carefully organized. Nothing random, nothing arbitrary.
What we would really love to understand is how the brain during development generates millions and millions of neurons, sends them to the right position in the brain, and then somehow instructs each of those individual nerve cells to form very, very specific connections with one another.
And here's some of the things that determine what kinds of connections are made and how durable they are, and if they're actually in the right areas of the brain where they need to be made. So the first one is the effects of the environment on the child, favorable, unfavorable, will interact with all the processes of neural development. And we just covered one of them. We just covered migration. So there are 7 more processes that are involved in the development of the nervous system that can be affected by this unfavorable environment that the child's exposed to. So we can go all the way from the neurogenesis to the migration to the actual removal of extra neurons that are getting in the way of the brain efficiency, and then go all the way through to processes like forming of synapses and the processes that involve, for example, the development of the long tentacles that reach out from the cells, the dendrites, the very fine fibers that are making connections. So these are all 8 of them. All 8 of those processes are affected by the environment in which the child is raised. So genetic and environmental principles influence all these processes. So we have genes working, and we also have environment working. We saw how important the environment was just by looking at the redirecting of the neurons coming from the optic nerve to the auditory cortex in an animal, in a simple animal, and how basically this environmental milieu that the axons were directed to was causing actually there were cell bodies in that area that are actually changing as far as their ability to transmit certain types of information. So they need both stable emotional attachments with people, caregivers, and touch from primary adult caregivers, and spontaneous interactions with peers. And this is another thing that you recognize, for example, with someone in the autism spectrum disorder, their inability to actually engage other people. So normally if you're in the grocery store and you see a 1-year-old or a 2-year-old in a stroller and you look at them, they'll invariably smile at you. Or if you smile at them first, they'll smile back. But if someone is somewhere in that autistic spectrum disorder, and this is an issue for them as far as sociality is concerned, you just get a blank stare. And then if they notice that you're looking at them, they'll avert their eyes. So, there's a lot of work being done in that area, and one of the possibilities seems to be, first of all, that it seems to be genetic. And the other part is that when you start teasing that apart, what genes are being expressed or not expressed, it has something to do, at least in part, with the adhesion molecules that actually hold the connections between the neurons together. So in order for those to remain stable, there are special bridges that are built between the 2 neurons that kind of allow them to more or less interlock, although they never actually touch the membranes, but these molecules will keep them together. So if the connections are lacking, brain development, both of caring behavior, this is empathy and compassion, and cognitive capacities can be damaged in a lasting fashion. All right, we'll take a quick look at migration. Oh, I know what okay. So I just want to do this first. So this is your cortex, and this is before we see the video piece of this. What you're going to see is that these are where the cells are being born in this area. This is the brain sectioned here. You see there's no bumps in the brain at this stage of development, but it's hollow and it's filled with cerebral spinal fluid, or what will become cerebral spinal fluid. And then this is lined with cells like this. So if we take this and put it down here, we see that the cells have a migration path to take that eventually brings them to one of these 6 layers of the cortex. And if they don't get to the right layer, they're not communicating with the neurons that they were designed to communicate with. And they're looking at this as a possible cause of, for example, things like schizophrenia. I mean, there are a lot of other things that are possibly associated with this. So inside the brain itself, for every neuron, you have like 10 helper cells. So this would be one of those. They're called glial cells. So they have these long fibers that go all the way from here all the way down to the bottom. And the neurons actually climb up the long projections, the long fibers of the glial cells to get to where they're supposed to be. Now, they know that if a mother is stressed during pregnancy, that the high levels of cortisol in the mother's blood actually impair the ability of these neurons to migrate and actually connect at the level they're supposed to connect with in order to have normal brain function. And there's all kinds of chemicals, neuroleptic drugs, psychiatric drugs have a big issue in this area. And you can just go on, with all the toxins in the environment. This is very apparent in Vietnam with the dioxin toxicity, that caused abnormal limb formation, as well as all kinds of cognitive problems with the babies in Vietnam. So I just pretty much explained this, so we don't need to spend any more time on that. So let's just take a look at it. Oops.
As the tiny fetus grows, the neurons make their way out from inside the neural tube to build the brain, layer upon layer, like an onion. The neurons follow a cellular pathway, as if they were traveling down a highway. They just grab hold of supporting cells called glia and propel themselves along.
They put their nucleus in the back of the cell, which makes them sort of fat in the back, and then they hold on to the guide wire, this glial fiber. So it's kind of like an inchworm as it moves along. And each little cell goes all by itself in what is a very, very vulnerable process. No other kind of cell has to do that, and it's just an amazing thing.
Neurons travel in waves, millions every day, embarking on a daunting expedition that scientists call migration.
It's an amazing phenomenon because it's as if they're going across the country. I mean, in terms of the distances relative to their size, they're making a huge odyssey through all kinds of foreign territory. And the most amazing thing about this migration is that they generally do it without mistakes. They're following cues along the way that are telling them exactly where to go.
For years, scientists wondered how the migrating neurons find their place in the brain. Do the neurons simply travel in herds, gliding down a glial highway which takes them to their final destination? Or do neurons do their own driving, each neuron genetically programmed to fulfill its own predetermined purpose?
We used to think that migration was just like delivering cells out a conveyor belt, and we just dump out the cells at the end. But now we know that's not the case.
It's a fascinating process. And just remember that when she mentioned the fact that this migration is dependent upon not only genetics but on environmental cues, the environmental cues are the molecules that are present in the area of migration that are to some extent determined not only by the nutrition in this case of the mother, but also other things that the mother may be taking, or stress response that releases all kinds of different molecules that can possibly impinge, in addition to the cortisol that can impinge upon the migration of the neurons. So when you have kids in a war-torn zone and women that are pregnant and they're under this constant stress, can you imagine living in a city that was being bombed all day, like in Iraq, and then at night you didn't get any rest because they were driving through the village with great big loudspeakers playing loud music, and you have a child that's sick and is trying to sleep, so you don't sleep, the child doesn't sleep, the child's going to have, there's no way you can escape abnormal development in an environment like that. So you're guaranteeing another generation of individuals that is going to not be able to function as a fully competent human being has the capacity to do if the development takes place in a way that's consistent